Hello everyone and welcome to this video. So in this video we are discussing this kinematics worksheet which is part of your past papers book volume number 1. This is supposed to be the second worksheet there. So let's go through these questions one by one, all the MCQs as well as the theory questions. Alright, let's start with this first one. Winter 23 paper 1-2 question number 2. The diagram shows the distance time graph of a car. The car is traveling along a straight road up a hill. So this is a distance time graph. How you are supposed to approach any and all questions related to graphs, especially in kinematics, is like this. So you see this is a distance time graph. So the first step is to just note the type of the graph this is. So this is a distance time graph. The second step is to see that since this is a distance time graph, what does the gradient and area of this graph represent? Now because this is the distance time graph, I know for a fact that the gradient is speed and the area does not hold any significance. And now the third step is to basically read the rest of the question and now try to infer whatever the examiner wants us to do with this graph. So this is a distance time graph. I can see this has a constant gradient because this is a line, and if this has a constant gradient, I infer that this graph has also a constant speed. Then it says the car is traveling along a straight road up a hill. So just like how this graph shape is coincidentally, the car would be traveling along this path. So it's going up a hill. Which quantity for the car is constant and greater than 0? Part A, acceleration. If speed is constant, this means that acceleration would be 0, right? Because acceleration is rate of change of velocity, or in this case, we can also say it's the rate of change of speed. So acceleration would be 0, but the question wants us to find something which is greater than 0. Part B, displacement. If it starts from some point and if it's just going up a hill on the straight road, it would also have some displacement, and as long as it is moving, the displacement would also be changing, it would be increasing. Part C, GPE. So GPE is mgh. Since the car is going up a hill, so h is increasing, hence mgh would also be increasing, so GPE is also increasing. This is also wrong. By process of elimination, D must be the correct answer, and this makes sense because this is, let's make some space. So kinetic energy is half mv square. So from here neither m nor v is changing, so all of this is constant, but it's also greater than 0. Question number 2, same paper, question number 3. It's of the same paper, Winter 23, paper 1-2. A distance time graph and a speed time graph show the motion of an object. How are the speed and acceleration of the object determined from these graphs? So speed is what? Speed is the gradient of the distance time graph, so it's this or this. And acceleration is the gradient of the speed time graph. Easy. Alright. Winter 23, paper 1-1, question number 2. This is a different variant. The diagram shows a distance time graph for a car traveling in a straight line. In which region is the car decelerating? Alright, so for deceleration, again I do the same thing. I know this is a distance time graph. I know that the gradient is speed. Now for deceleration to be happening, this means speed must be decreasing, and as a result gradient is decreasing. So I'm looking for a curve which has a decreasing gradient shape. This curve must be flattening out. So if I see here in this portion the gradient is increasing, this is basically the part where the car would be accelerating. Here the gradient is constant, this is constant speed. Here the gradient is decreasing, this is what we want. And at D the gradient is 0, so this basically means the speed is 0, so the car is at rest. A car begins to move, it speeds up until it reaches a constant speed. What happens to the acceleration and what happens to the velocity of the car? Again, this question is one which has been repeated a lot of times over the past some years of our papers. This is just the most recent occurrence. So if it speeds up, this means that it must be accelerating, so acceleration must be changing. So it has to be this or this, and acceleration by default, it says that it speeds up until it reaches a constant speed, so velocity must also be changing. So it's A. Alright, so before this question, there used to be a lot of debate on whether tangents and using them for graphs is really part of the syllabus or not. But when this question came in, then this was really clarified that yeah, this is part of the syllabus. Curved line on the distance time graph shows the motion of a toy car. Straight line is a tangent to the curve at 10 seconds. Right? This is the tangent, the dotted line. What is the speed of the toy car at 10 seconds? Again, I know this is a distance time graph. I know that the gradient is speed. So if I need to find the speed at 10 seconds, I basically have to find the gradient, right? So if I just zoom into this graph, I just really need 2 points. And whenever working with graphs, try to choose points at the extremes because that's obviously the ones which are easier to read. So this point, this value is 3, so one coordinate that I have is 0, 3, and the other coordinate, if I look here, is 10, 6. So 0, 3, 10, 6. Then we just do change in y1, change in y over change in x. So 6 minus 3, y2 minus y1 over 10 minus 0, x2 minus x1. So 3 over 10 is 0.3 meters per second. A speed time graph for the journey of a car is shown. This is a speed time graph and you have to reduce the distance time graph. Alright, so I can see that this is a speed time graph. Again, let's see what this is. So let's write down what we know. So it's easier to go from a distance time to a speed time because we know that the gradient of a distance time graph would be speed. So here is the approach that I'm using. Even though the question gives me a speed time graph, I'll be going from the distance time graph, and I know that the gradient is speed. Now I start to think. For a distance time graph, I can see that the gradient or the speed here is increasing. This is accelerating. So this means that in the initial part of the graph, I must have a gradient which is increasing, right? So it must be getting progressively steeper. So it cannot be this because here the gradient is decreasing, here the gradient is decreasing as well. So it's going to be either B or D. So for the first part, the gradient is increasing, and then as the speed becomes constant, this means that the gradient would become constant, which means that the shape turns into a line. So gradient is constant, right? So gradient becoming constant means this. This is not true because a distance time graph being horizontal means gradient is 0, which means speed would be 0, but speed's not 0 here. A car travels at 60 kilometers per hour on a straight road. The road is dry. The driver applies the brake. Suddenly, the table shows the thinking, braking, stopping distances. Same car is driven by the same driver at 60 kilometers per hour on the same road when it is wet. The driver applies the brake again. What is the effect of the wet road on the thinking, braking, and stopping distances? If speed is the same and nothing else is changing, then we know that the road conditions would not have any effect on the thinking distance. So no change, no change. braking distance would increase, and since stopping distance is thinking distance plus braking distance, this would also increase. A ball starts from rest and rolls down a steep slope. The ball then rolls along rough horizontal ground. Which graph shows the speed of the ball at different times? So it starts from rest, so we know that initial velocity must be 0. So it cannot be this, right? From starting from rest. And then it rolls down a steep slope. So if it's rolling down a steep slope, so basically the weight of the ball itself would be making it accelerate, right? So it's accelerating, which is happening in all of A, C, and D, and then it rolls along rough horizontal ground. So if it rolls along rough horizontal ground, it would now be decelerating, basically because of this word right here, rough ground, because it's going to introduce friction, and friction makes things decelerate. So if it's going to decelerate, then the graph must be going down. So it cannot be this, because here it shows speed as constant for the second stage, and neither would it come instantaneously to rest, it would just be slowing down. The diagram shows a car at the moment that the driver sees a hazard ahead. Thinking distance, braking distance, which expression is equal to the stopping distance? So that's just the sum. Super easy. Thinking plus braking distance. Alright, let's zoom in, zoom out, and look at this one again. An object is accelerating along a straight horizontal track. Acceleration is uniform. Which speed time graph represents the motion of the object? So speed time graph, gradient is acceleration. So if here the acceleration is constant, so this means I'm looking for a case of a constant gradient as well, and lines have a constant gradient. I have two lines here, so it cannot be a curve, but this line does not have any gradient. This is zero gradient, so it's just A. Which part of the distance time graph shows the fastest constant speed? So again, distance time graph, second constant speed, so I know that gradient is speed. So for the fastest speed, for the speed to be as large as possible, the gradient must also be maximum. We really have two parts where the gradient is not zero, because the gradient is zero on the horizontal lines. So it's A versus C, which is steeper, and the simple answer is that's C. Question number 12. A driver drives a car at uniform velocity along a road. The driver sees a hazard and applies the brakes. What is the car's motion as it travels through the thinking distance and as it moves through the braking distance? So because it was at uniform velocity before applying the brakes, then that means that through the thinking distance, which is basically the distance traveled during the reaction time, it would be going at uniform velocity, and after the brakes, it would be decelerating. A skier slides down a slope. Diagram shows how his speed varies with time. What is his average acceleration during the 6 seconds? Now, whenever you're doing a question, and if you see this word average written anywhere, so this means that instead of this normal formula where you would have change of something over change of something, you now just take totals. Now, what do I mean here? If I was just talking about a general acceleration formula, instantaneous acceleration, it's change in velocity over change in time. But if I'm talking about average acceleration, this would now be the total velocity, like the final velocity, over the total time taken to reach that velocity. Right, so basically I'm thinking when we are finding averages, I'm thinking about this as one straight line. Right, so the final velocity which is reached is 26 divided by 6, which turns out to be 4.3 meter per second square. Alright, let's have a look at this one now. A boy starts at P, walks 3 meters due north from P to Q, then 4 meters due east from Q to R. What is the shortest distance that he must now walk to have an overall displacement of 0? So this is 3 meters, this is 4 meters, and the way that the displacement could be 0 is that if the starting and the ending position are the same. So what he could do is he could walk exactly in the reverse of how he walked previously, but that's not going to be the shortest distance he could walk. The shortest distance is if he does not make any turns, and from wherever he is, he just walks back in a straight line to P. So in this case, the answer would be C, which is 5 meters. Alright, so this is a sort of a weird question in the sense that usually we do not have a we know that a distance time graph cannot descend, but if you think about what this is, a train sets off from a station at time t equals to 0. Graph shows how the distance between train and station varies with time. So because we are looking at the distance from the station of the train, this means this is really a displacement time graph. Now this is why it's weird, because displacement time graphs are technically not part of the syllabus. So we can see that first the displacement is increasing. So this must mean we are going away from the station, and after that the displacement is decreasing, which must mean that we are coming back towards the station, right? And then the displacement also becomes 0. Which statement about the movement of the train between time t1 and t2 is correct? So t1 and t2, the displacement is decreasing, right? So it's definitely moving towards the station back again. So towards or towards. And now if I think about this, is this so basically with displacement time, just like how with distance time the gradient of the distance time graph was speed, similarly the displacement time graph, the gradient of that would be velocity. So what's happening to the gradient from here versus here? So if I just make some dotted lines, so this would be the gradient here, and this is how the gradient would be here. So this gradient is definitely steeper at T2. So this means that from T1 to T2 it has sped up. There has been an increase in velocity. So the speed is also then increasing. Let's go on to another question. The speed time graph for a car's journey is shown. During which speed of the journey is the car moving with non-uniform acceleration? Again, this is a speed time graph. The gradient of this is acceleration. And for non-uniform acceleration, non-uniform means not constant acceleration, and a not constant acceleration would also lead to a not constant gradient, which means we are just looking for a curve, which is very obviously C. This question we've done above, this is repeated. Alright, let's have a look here. Two cameras are a known distance apart. Alright. The exact time that a vehicle passes each of the cameras is recorded. What can be obtained from the information? So this is basically like we have some speed cams, and this is camera 1, this is camera 2, and we know when the car passes this camera 1, so we know sometime t1, and similarly we know sometime t2 when he passes the second camera. So if I think about this, I know some total time, and we also know the distance. So I know the total distance, I know the total time. Do I know of a formula that links these two quantities? And the answer is yes, that is average speed, which is total distance over total time. Now what is average acceleration really? If I had this functionality which could also tell me the speed of the car at C1 and the speed of the car at C2, then I could also get the change in speed, and then dividing by the change in time I could get the average acceleration. But I don't have that luxury here, So this cannot be the answer. Max acceleration of the vehicle. For max acceleration, I would need at every time, because acceleration is rate of change of velocity, then I need something which gives me the acceleration at every instant as the car is going from here to here. Then the total time would not work for me. I would just need the maximum gradient. So maybe if I have a graph, then if I calculate the max gradient of a speed time graph at that point, then it could tell me the max acceleration, right? Now max speed of the vehicle might also seem tempting to a few, but think about it this way, that if the car entered this region of the camera C1 and it sped up, and then it slowed down, and then it sped up, and then it slowed down, would this total distance over total time tell me these changes in speed? And the answer is no. Again, for that case as well, I would need a graph, and I would need this equation. And with this equation and with those different data values, then I can find the steepest gradient of a distance time graph. That could be the max speed, right? So I can only find the average speed in this case. So neither this nor this. Question number 19. The graph shows a short journey. It's a speed time graph. What is the greatest speed reached? This question is definitely easier than it seems. It's a speed time graph and you just need the greatest speed reached. So for this, you just see that the greatest speed is 3 meters per second. Never go up to 4. Yeah. Alright, winter 19, paper 1-2, question 6. The graph shows the speed of a car. How the speed of a car varies with time. So step 1, speed time graph. Next, the gradient of this graph is acceleration. Which statement about the acceleration of the car between times 10 and 20 is correct? So 10 and 20, I can see that the speed has now become constant. So this means the acceleration is 0, right? If the speed is constant, then the acceleration is 0. Or you can also use the gradient approach, that since this is a horizontal line, gradient is 0, which implies acceleration is 0. If you did not read the question properly, then you could have also been tempted to say that because the graph is flattening out here, the acceleration is decreasing, but it was asking just about what's happening between these times. Alright, the diagram shows the distance time graph for a moving object. Now, if you just look at this question and the previous one, it might seem similar, but that's what step 1 helps us do, which is that the first step is to identify the type of the graph. So the graph shapes may look similar, but why do teachers stress so much on not memorizing the graph shapes and rather just trying to analyze them the correct way? Is because the same graph shape on different axes can have entirely different meanings. So this is a distance time graph, and we know that the gradient here is speed. And now if I look at this, so initially the gradient is decreasing, this means speed is decreasing, and then the gradient becomes constant, so the gradient becomes 0, so the speed becomes 0, right? So this is something which is decelerating and then comes to rest, right? So let me write this down here, decelerating to rest. Now let's see which scenario here fits this description. A ball thrown vertically upwards, falling back to the thrower. This is never at rest. A car starting from rest, speeding up, not at rest. A rock dropping from a high cliff, falling into the sea below. A high cliff basically tells us this, that this is falling in air and it has reached terminal velocity. And this might be the most tempting option here. But again, you remember that this is a distance time, not a speed time graph. If this graph was a speed time graph, this option would have been fine. But this is not a speed time graph, because here the speed becomes constant, however here the speed becomes 0. And now if you look at D, then that makes sense, a train braking to a halt as it stops. A cyclist traveling in a straight line at 8 meters per second accelerates to 12 meters per second in a time of 6 seconds. Which expression gives the cyclist acceleration? So A equals V minus U over T. Final velocity is 12, starts out from 8. All this happens in a time of 6. So that's D. Pretty easy. Now this one, a woman runs 2 kilometers from X to Y in 20 minutes and then rests at Y for 10 minutes. She then takes 10 minutes to run 1.6 kilometers from Y to Z. What is the size of her average velocity? For average velocity, I'll be using the average displacement. So do I have a line here which connects X all the way to Z? I do. That is 2.4 kilometers. This is average displacement here. Sorry, not the average displacement, the total displacement here, divided by the total time. So the total time is 20 and 10. And then the problem happens, do we take this or not? Because she was resting at Y. And the answer is we would take it because it's total time. We don't care about whether she was resting or not. All of the time goes into the denominator, and the answer turns out to be option A. Another good and a different type of question. The table shows speeds of 4 bodies A, B, C and D and how they change with time. Which body has an acceleration that is not constant? So acceleration is the rate of change of velocity. What is constant acceleration? Constant acceleration is when something is speeding up in such a way that the speed increases by the same amount each second. Now if I do this, and all of this data is given at 1 second intervals, right? So 0 to 1 this increases by 1, 1 to 3 this increases by 2, and further if I want to confirm 3 to 6 this is also increasing by a different amount. This means this is not constant acceleration. Now let's go on to the rest of the options and see why those have constant accelerations. 0 to 2 is plus 2, plus 2, plus 2. 0 to 3, plus 3, plus 3, and plus 3. And 5.5 to 6.5 plus 1, plus 1, plus 1. So all of the other options have constant accelerations. A is the only one which has a not constant acceleration. Alright. A cyclist takes a ride lasting 250 seconds. The graph shows how the distance from the starting position varies with time. So it's a distance time graph. Gradient is speed. Now let's go on and read the rest of the graph, the rest of the question. What is this average speed for the whole journey? So average speed is total distance over total time. So the final distance is 300 divided by 250. So this turns out to be 300 over 250 should be 1.2. The minimum braking distance for a car is tested on dry road. The test is then repeated on a wet road. What happens to the braking distance and to the frictional force? Again, the friction must be decreasing on the wet road. So friction decreases, and because the friction decreases, the force decreases, hence the acceleration decreases. So the same car would now be taking longer to come to rest, and in doing so it's traveling more distance. So it's C. Which speed time graph represents the motion of a railway train making a short stop at a station? So if this is a speed time graph which is making a stop, this means speed should become 0. In this one, speed is not 0, speed is not 0, speed is 0, speed is not 0. So that's why it's C. An object travels for 20 seconds with a constant speed of 10 meters per second. And then for the next 10 seconds it accelerates uniformly to 20 meters per second. What is the total distance traveled by the object in 30 seconds? So this is again a speed time graph. So let's write this down. Speed time graph. And the area under, this is what we are going to be using here, is distance. right? Because the distance has been asked of us. So for the area under, this now seems like quite a complex shape, so you might split this down in many different ways. For example, how I'm thinking is if we make it into these two shapes A and B, so this being the entire rectangle A and this small triangle B. So for A, I would say this is just 10 times 30, which is 300. And for B, I would say this is a triangle. Base is 10, height is also 10. So half base into height, half 10 into 10 is going to be 50. And you add both of these, you get 350 meters. Alright, so we've done a question something like this, if not exactly this. The speed time graph represents a short journey, which distance time graph represents the same journey. So you just use this, that since you have distance time graphs to select here, so this is distance time and the gradient is speed. If you look at the graph above, speed is increasing, hence the gradient should increase. So this must be a curve which is getting steeper, hence it's A. Let's try out this one. The diagram shows the speed time graph for an object moving with uniform acceleration, distance traveled in the first 4 seconds. Also, as a general advice, just forget this formula that you've ever studied before, which is distance equals speed multiplied by time. Just use area under the graph whenever you see questions related to graphs, because that's also going to work out in cases where those formulas can apply. But with a case like this, if you use speed times time, the answer is going to be wrong. Because if I were to just shade this area here to show what the distance traveled is, it's all of this area under the graph. So if I think about this, this is just a triangle. So half, base is 4, height is 6, so 6 times 2 is 12 meters.